It feels ordinary, transparent, quiet. Completely familiar. You lift it, take a sip, and nothing about the experience seems mysterious. Your brain classifies it instantly, water in a glass, a simple everyday object. But if you pause for a moment and ask a deeper question, what is actually inside this glass? The answer begins to unfold into something far stranger than it appears. Water is made of molecules. Each molecule contains atoms, 2 hydrogen atoms and 1 oxygen atom. Already we are far beyond anything you can see with your eyes. Inside those atoms are electrons moving around a nucleus. Inside the nucleus are protons and neutrons. Inside those are even smaller constituents called quarks. And when physicists tried to understand what those particles really are, they discovered something unsettling. They are not quite particles. At the deepest level, modern physics describes them as excitations of invisible fields that fill all of space. Even in what we call empty space, those fields are still there, fluctuating quietly. The glass of water in your hand is not really a collection of tiny solid balls. It is an intricate pattern of vibrating fields. And if that already sounds strange, it gets stranger the deeper physicists look. Few scientists were as honest about this strangeness as Richard Feynman. Feynman was one of the most important physicists of the 20th century and a key contributor to quantum mechanics, the theory that describes how nature behaves at extremely small scales. But what made Feynman unusual was not just his brilliance, it was his intellectual honesty. Where many scientists tried to wrap quantum physics in neat philosophical explanations, Feynman refused to pretend we understood more than we actually did. He once made a statement that still surprises students today. I think I can safely say that nobody understands quantum mechanics. That statement wasn't meant as a joke, and it wasn't false humility. It was a precise observation about the situation physicists find themselves in. Quantum mechanics is arguably the most successful scientific theory ever developed. Its predictions match experiments with extraordinary accuracy. Technologies like lasers, transistors, and modern electronics exist because the theory works so well. But working mathematically is not the same thing as making sense intuitively. We can calculate what will happen, but explaining why reality behaves that way is another matter entirely. Our everyday intuition tells us that objects have definite positions. A baseball travels along a clear path. A marble rolls across the floor in a predictable way. But at the microscopic level, nature refuses to follow these simple rules. Particles behave like waves. Events occur only with probabilities. And in some situations, the universe seems to explore multiple possibilities at the same time before settling on a single outcome. Feynman believed the most honest way to teach physics was not to hide these uncomfortable facts. Instead, he wanted students to confront them directly, because the deeper we investigate the universe, the clearer it becomes that reality does not resemble the world our senses evolved to understand. And the first step toward grasping this strange truth begins with one deceptively simple experiment, an experiment that reveals the central mystery of the quantum world. There is an experiment in physics so simple that it can be explained in a few sentences, yet so strange that it has puzzled scientists for more than a century. Many physicists consider it the clearest window into the deepest mysteries of quantum mechanics. This experiment is known as the double-slit experiment. At first glance, the setup looks almost trivial. Imagine a flat wall with 2 narrow openings cut into it. These openings are the slits. Behind that wall is a large screen that can record where tiny particles land. Now imagine you have a device that can fire extremely small particles toward the wall. For the sake of discussion, let's say those particles are electrons. If you rely on everyday intuition, you would expect something very straightforward to happen. Each electron travels forward, passes through one of the slits, and strikes the screen behind it. If thousands of electrons are fired, you would expect them to pile up in 2 clusters directly behind the slits. 2 openings should produce 2 bright bands on the screen. This expectation comes from our everyday experience with objects behaving like little projectiles. Throw sand through 2 gaps in a fence, and the sand will land in 2 piles behind those gaps. So physicists performed the experiment to confirm this simple prediction. But the result was not what anyone expected. Instead of 2 bright bands appearing on the screen, A series of alternating bright and dark stripes slowly emerged. The pattern looked like evenly spaced bars stretching across the screen. This pattern is called an interference pattern. Interference patterns appear when waves overlap and interact with one another. When two water waves meet, their crests and troughs combine. Some places reinforce each other and become stronger. Other places cancel out and disappear. The result is a repeating pattern of bright and dark regions. Light produces exactly the same kind of pattern when it passes through two narrow slits. This was demonstrated long ago by Thomas Young, whose experiments helped establish that light behaves like a wave. But electrons are not supposed to be waves. Electrons are particles. They have mass, charge, and can collide with other objects. In many experiments, they behave exactly like tiny solid objects. Yet in the double-slit experiment, they somehow create a pattern that only waves should produce. This was already deeply confusing, but physicists pushed the experiment further. They wondered whether the strange pattern might come from electrons interacting with each other. Perhaps the particles were somehow bumping or influencing one another on their way through the slits. So they changed the experiment. Instead of firing a continuous stream of electrons, they fired them one at a time. A single electron was launched toward the slits. Then they waited until it hit the screen before firing the next one. Under these conditions, there should be no possibility for electrons to interfere with one another. Each electron travels alone through the apparatus, yet something remarkable still happens. Each individual electron lands on the screen as a tiny dot, but as thousands of these dots accumulate over time, the same interference pattern slowly appears. Bright stripes. Exactly the pattern produced by waves. The implication is astonishing. Each electron somehow behaves as if it travels through both slits simultaneously and interferes with itself. Not with another electron, with itself. This conclusion challenges nearly every assumption we have about how objects should behave. Instead of choosing one path, the electron appears to explore multiple possibilities before finally arriving at a single point on the screen. The deeper physicists investigated this phenomenon, the more it became clear that the experiment was not just unusual. It was revealing something fundamental about how reality itself operates. At this point, the situation begins to feel deeply uncomfortable because the natural response is to look for a hidden explanation that restores common sense. Perhaps the electron secretly goes through one slit, but something about the experiment distorts the pattern afterward. Maybe the measuring screen creates the interference. Or maybe the particles are bouncing off invisible disturbances in the apparatus. Physicists thought of these possibilities too, and they designed experiments to test them. The most obvious idea was simple: watch the electron while it passes through the slits. If we could observe which slit the electron actually travels through, the mystery should disappear. The electron must go through either the left slit or the right slit. Once we see the path, the pattern on the screen should become two ordinary bands. So detectors were placed near the slits to observe the electron's path. And something remarkable happened. The moment physicists measured which slit the electron passed through, the interference pattern vanished. Instead of the striped wave pattern, the screen showed exactly what common sense predicted from the beginning: two simple clusters behind the slits. In other words, when the electron is not observed, it behaves like a wave that passes through both openings. When the electron is observed, it behaves like a particle that chooses only one path. This strange behavior lies at the heart of what physicists call wave-particle duality. Electrons, photons, and many other microscopic entities are not purely particles or purely waves. They possess properties of both, depending on the situation. But even that description can be misleading. It suggests that the electron is switching between two different modes of behavior. In reality, quantum theory describes something even more abstract. Instead of assigning the electron a definite position or path, physicists describe it using a mathematical object called a wave function. The wave function does not represent a physical wave in space like a ripple on water. Instead, it represents a spread of probabilities. Before a measurement occurs, the electron is not located at a single point. Instead, there is a cloud of possible locations where the electron might be found. The wave function spreads through both slits, explores the region beyond them. and interferes with itself just like overlapping water waves would. This interference produces regions where the probability of finding the electron is high and regions where the probability is extremely low. When the electron finally strikes the screen, the wave function collapses and produces a single dot. But that dot appears in a place consistent with the probability pattern created by the wave. Over time, as many electrons are detected, the pattern gradually emerges. Bright regions where probability was high. Dark regions where probability nearly vanished. But the truly unsettling part is what happens when we attempt to observe the path. The act of measuring which slit the electron passes through forces the wave function to collapse earlier. The spread of possibilities disappears, and the electron behaves like a localized particle instead. The interference pattern can no longer form. This raises a question that still echoes through modern physics. What exactly counts as a measurement? Is it the presence of a detector, the interaction with another particle, or the irreversible recording of information somewhere in the universe? Despite decades of research, physicists still debate the precise meaning of this process. And this is why many scientists, including Richard Feynman, insisted that the double-slit experiment reveals something profoundly mysterious about nature. The universe appears to behave as if possibilities are real physical ingredients of reality. Not just things that exist in our imagination, but things that actively influence how events unfold. When physicists first encountered these strange behaviors, many tried to rescue a familiar picture of reality. The hope was that somewhere beneath the equations there existed a simple story, a hidden mechanism that explained what the particles were actually doing. But Richard Feynman approached the problem differently. Instead of forcing the universe to match human intuition, he focused on building a mathematical framework that described exactly what experiments showed. From this effort came one of his most beautiful ideas, known as the path integral formulation. To understand the idea, imagine something familiar. Suppose you throw a baseball from your hand to a friend standing across the field. The ball follows a smooth arc through the air. If you were asked to describe the path, you could draw a single curved line connecting the starting point and the final point. Classical physics assumes that objects move along one definite trajectory like this. But Feynman suggested that when we look at nature on extremely small scales, this assumption breaks down. Instead of traveling along one path, a particle behaves as if it explores every possible path between its starting point and its destination. Not just a straight line, not just a smooth curve predicted by classical physics. Every path, imagine all the strange possibilities. A path that wiggles back and forth like a scribble. A path that loops around in circles before reaching the destination. A path that briefly travels far away and then returns. Even paths that seem absurd contribute to the final result. According to the mathematics of quantum theory, each of these paths carries a tiny contribution to the particle's behavior. These contributions combine with one another through interference, much like overlapping waves. Some paths reinforce each other, others cancel out. When all of these possibilities are added together, something remarkable happens. The bizarre paths tend to cancel each other through destructive interference. Only a narrow group of paths near the classical trajectory reinforce one another strongly. The final result is that the particle usually appears to travel along the path predicted by classical physics. This is why everyday objects behave in predictable ways. A thrown baseball does not visibly explore millions of strange routes through the air. The interference between those possibilities eliminates almost all of them, leaving only the familiar arc. But at the scale of electrons and photons, the situation changes dramatically. The cancellation between paths becomes less complete, allowing the strange quantum possibilities to reveal themselves. The particle begins to display behaviors that seem impossible from a classical perspective. In this view, the double-slit experiment becomes easier to interpret mathematically. When an electron approaches the barrier with two slits, the wave, like probability, does not choose one slit or the other. Instead, the electron explores paths that pass through both openings and countless other variations as well. Each path contributes a small probability amplitude. These amplitudes combine and interfere with one another, producing the familiar pattern of bright and dark stripes on the screen. The interference pattern is not created by the electron splitting into pieces or physically dividing itself. It emerges from the mathematical combination of all possible paths the electron could take. Feynman's formulation did not remove the mystery of quantum mechanics, but it provided a powerful and elegant way to calculate the behavior of particles. In fact, the approach became central to modern quantum field theory, which describes how fundamental particles interact. Yet even Feynman admitted that the deeper meaning behind these calculations remains elusive. The mathematics works with astonishing precision, but the picture it paints of reality is profoundly strange. It suggests that the universe may not be built from particles following single paths through space, but from a vast landscape of possibilities interfering with one another before any event finally occurs. By the time physicists had developed the modern framework of quantum mechanics, they possessed a theory capable of predicting experimental results with astonishing accuracy. The equations successfully describe the behavior of atoms, electrons, photons, and many other microscopic systems. Entire technologies, lasers, semiconductors, and much of modern electronics depend on these predictions working exactly as expected. Yet something uncomfortable remains at the center of the theory. The mathematics tells us what will happen, but it does not tell us what is actually happening underneath. This distinction is subtle but important. In many areas of science, theories offer both prediction and explanation. Newton's laws, for instance, allow us to calculate how a planet moves, and they also provide an intuitive picture of forces acting on objects. Quantum mechanics is different. The equations describe probabilities. They give precise rules for calculating the likelihood that a particle will appear at a particular location or have a particular energy. But when we ask what the particle is doing before we measure it, the theory becomes strangely silent. This is where many physicists, including Richard Feynman, urged caution. Feynman believed scientists should resist the temptation to invent comforting stories that go beyond what experiments actually reveal. In the formal mathematics of quantum mechanics, a particle is described by a wave function, a spread of probabilities that evolves smoothly over time. When a measurement occurs, that wave function appears to collapse, producing a definite outcome. But the theory itself does not explain why this collapse happens. It simply tells us how to calculate the probabilities before the measurement. To deal with this conceptual gap, physicists develop various interpretations of the theory. One of the earliest and most widely taught is the Copenhagen interpretation. This view suggests that the wave function represents our knowledge of a system rather than a physical object. According to this interpretation, the act of measurement updates that knowledge and produces a definite result. However, this explanation raises new questions. What exactly counts as a measurement? Does it require a conscious observer? Or is any interaction with the environment sufficient? Other interpretations attempt to answer these questions differently. One famous example is the many worlds interpretation, which proposes that the wave function never collapses at all. Instead, every possible outcome occurs in a vast branching structure of parallel realities. In this picture, when a quantum event has multiple possible outcomes, the universe splits into different branches, each containing one of those outcomes. This idea removes the need for wave function collapse, but it introduces an entirely different kind of strangeness, an enormous number of parallel universes constantly diverging from one another. There are other interpretations as well: pilot, wave theories, objective collapse models, and several more, but none has been universally accepted. What all of these interpretations share is an important feature. They produce the same experimental predictions. This means that, at least with current technology, there is no clear experiment that can determine which interpretation, if any, correctly describes reality. And this brings us back to the uncomfortable truth that Feynman emphasized. Physics has discovered a mathematical framework that predicts nature with incredible success. But the deeper meaning behind that framework remains unclear. We know how to calculate the behavior of quantum systems. We know how probabilities evolve. But the question of what reality actually is beneath those probabilities remains one of the most profound open questions in science. Part of the difficulty in understanding quantum reality may not lie in the universe itself, but in the limitations of the human mind. The way our brains interpret the world was shaped by millions of years of evolution in an environment where survival depended on dealing with objects that move slowly and predictably. Humans evolved to judge distance, track motion, throw tools, and avoid danger. Our senses are tuned to detect patterns in the everyday world of rocks, trees, water, and animals. None of these experiences prepared the brain to understand phenomena occurring at the scale of atoms. Because of this, our intuition is built around what physicists call classical physics. We naturally expect objects to have definite positions and follow clear paths through space. If you toss a stone across a pond, you expect it to travel along a single arc and land at a specific point. The stone never takes multiple routes simultaneously, and it never behaves like a probability wave. But the deeper scientists investigate the structure of matter, the more it becomes clear that this familiar picture is not fundamental. At the microscopic level described by quantum mechanics, the basic ingredients of reality behave in ways that defy the expectations built into our brains. Particles do not always possess definite positions. Instead, they are described by probability distributions that spread through space. These probabilities evolve according to precise mathematical rules, but the underlying picture is nothing like the motion of ordinary objects. Even the concept of a particle becomes slippery. In modern quantum field theory, what we call a particle is actually a localized vibration in a field that fills all of space. Electrons are excitations of an electron field. Photons are excitations of an electromagnetic field. Every point in space contains these fields, quietly fluctuating even when no particles appear to be present. This means that the solid objects around us are not truly solid in the way our senses suggest. The atoms inside a table are mostly empty space, held together by electromagnetic interactions between electrons and nuclei. What feels like solidity is actually the resistance of these quantum fields preventing atoms from passing through one another. To a human observer, the table appears stable and definite. But on the microscopic level, it is a restless system of moving particles and vibrating fields. Our brains smooth over this complexity. Instead of perceiving trillions of microscopic interactions, we experience a simplified version of reality that is easier to navigate. This simplification works perfectly well for everyday life. It allows us to build tools, communicate, and survive in our environment. But when we try to apply the same intuitive reasoning to quantum phenomena, we run into trouble. Many of the concepts used in quantum mechanics, superposition, probability amplitudes, interference, have no direct counterpart in ordinary experience. As a result, they feel unnatural even when the mathematics describing them is perfectly clear. Physicists sometimes say that if quantum mechanics seems strange, it is because we are trying to force nature into mental categories that were never designed to handle it. This idea was expressed repeatedly by Richard Feynman. He often reminded students that the goal of physics is not to make the universe comfortable for human intuition. Instead, the goal is to describe nature as accurately as possible, even if the resulting picture feels unfamiliar. The difficulty we experience when thinking about quantum theory may simply be the result of confronting a level of reality that lies far outside the conditions in which human intuition evolved. As physicists explored the strange predictions of quantum mechanics, many hoped that eventually a clearer, more intuitive picture of reality would emerge. Perhaps quantum theory was only an approximation of a deeper framework that would restore the familiar ideas of definite particles and well-defined paths. But over time, the evidence continued pointing in the opposite direction. The equations worked exactly as they were written. Experiments repeatedly confirmed their predictions. Yet no simpler mechanical explanation appeared underneath them. For Richard Feynman, this situation led to an important philosophical lesson about the nature of scientific knowledge. Science is not the same as explanation in the everyday sense. Instead, science builds models that describe patterns in nature. These models allow us to predict what will happen in future experiments. If the predictions match observation, the theory survives. If they fail, the theory must be revised or replaced. But matching observations does not guarantee that we have discovered the ultimate mechanism behind reality. Feynman often illustrated this idea with simple examples. Consider gravity. Isaac Newton's theory accurately predicts how planets move through space. Using his equations, Astronomers can calculate the motion of the moon or the trajectory of a spacecraft with extraordinary precision. Yet Newton himself admitted that he did not know why gravity exists. His theory describes how gravitational attraction behaves mathematically, but it does not reveal the underlying cause. Centuries later, Albert Einstein proposed a deeper description through the general relativity, where gravity emerges from the curvature of space-time itself. Massive objects bend the geometry of space and time, and other objects move along those curved paths. This picture replaced the earlier idea of invisible forces acting across empty space. But even Einstein's theory does not answer the ultimate question of why space-time should behave this way. It provides a more accurate description, yet the deeper reason remains elusive. Quantum mechanics may represent a similar situation. The equations tell us how probabilities evolve. They predict the outcomes of measurements with remarkable accuracy. But when we ask what reality is doing behind those probabilities, we encounter silence from the theory itself. Feynman believed this silence should not be filled with speculation disguised as certainty. Instead, he argued that scientists should clearly distinguish between what is known and what remains mysterious. This attitude reflects one of the most important principles of scientific thinking: intellectual humility. Nature does not promise to provide explanations that match human expectations. Sometimes the best we can do is identify reliable mathematical patterns that describe how the universe behaves. And in the case of quantum physics, those patterns suggest a world that is fundamentally different from the one our senses present to us. Particles appear to explore many possibilities at once. Events occur according to probabilities rather than predetermined outcomes. And the familiar solidity of objects emerges only at large scales, where countless microscopic interactions average together. The lesson is subtle but powerful. The success of a theory does not necessarily mean we have uncovered the final layer of reality. It simply means we have found a language capable of describing nature's behavior, at least for now.